Thanks for coming. So for the host today, you may have seen that we are squatting here in the break room. We have a sixth meeting for the next today, which is an ongoing project where IETR is part of the project. And this is with the ESL team at EPFL and Denisa is Denisa, who's part of ESL, is going to present the work at ESL and including Sims project, so you all know what we are working on.
Okay, thank you for the introduction, Mikhail. So I'm a postdoc at the Embedded Systems Lab, and I'll be presenting mostly the work that I'm doing, Ruben as well, and some other people in the lab. Especially X-HEEP. I heard that this is something that some of you are working on, so I wanted to give you more insights on how to get started with it. Yeah, then if you have more questions, we can just stop at any point and discuss. We also have Miguel online. If there are questions, I think he can back me up on some of the projects that I'm not very heavily involved with. So yeah, that's it. The topic of the talk is going to be mostly on co-design, and the main focus is efficiency, sustainability, and then we're going to go through some quite spread type of applications from AI, HPC, which is basically Sims project, and also IoT. This is the Embedded Systems Lab in a nutshell. So here you have me, Ruben, you know him. This is the big boss, Professor David Atienza. It's a big lab and growing. So I'm just one of the 12 postdocs there, and there are some 30 students doing their PhD. Yeah. Yeah, he has a very busy schedule, you can bet. Yeah, so in a nutshell, I'll start with sustainable computing. CODC is going to be the first topic. It's a study we did on carbon and economy optimization for data centers. It's something that sprouted from the Sims project, but then we didn't have data for rate astronomy pipelines in data centers, so we jumped into AI benchmarking to validate our study analysis. So you'll see some insights from that. And yeah, the other topic is co-designing energy efficient edge AI. So it's mostly IoT, wearables, this kind of applications, and what are the methods that we have developed in the lab, and what is already open source that you can use. And finally, some discussion, but I want to leave it for the end. Just interrupt me. Okay, so why is sustainability so important? Computing is everywhere, it's growing, and if we don't do it efficiently, it's not gonna scale. Well, it's especially important with the AI revolution. Like back in the day, we could just do classification, identify a few things from our environment, but now we can generate crazy monkeys driving a car, or whatever you want. But this has a cost, and it's an important cost in energy at the data center level, and there is a huge concern about how much emissions all of this computation is producing, both at the operational data centers. So here on the left-hand graphs, you see projections of the energy mix from the International Energy Organization, and you see that the energy that's going to be consumed by data centers by 2035, it's gonna more than double to what we have right now. But for some reason, the screen stopped sharing. Let's go back to it. Can you see it? Yes. Yeah, so I was saying that the energy demand for data center is projected to grow a lot. And this is mostly because of AI. There's lots of investment in building new data centers for AI. And this also has an impact, so it's not just the operations, the electricity, and having a mainly carbon-based generation of electricity. It's also the production of new platforms, GPUs, TPUs. You see here a report from IMEC, I'm not sure if you're familiar with IMEC. It's like top leading research. I wouldn't call it a center because they have multiple locations across Europe, but they're at the frontier of technology design. And what they see that the embodied emissions for the new technologies is also growing up. So, okay, we want to reduce emissions according to the Paris Agreement for all the domains that we have activities as humans, including computing. But the trends in computing and the demand of energy and the generation of carbon is going the opposite direction. So, okay, what can we do about it? How can we reduce the emissions in data centers? And well, we mostly work in computer architecture and systems design, co-design. So we look at things like this over here. So we look at CPUs, GPUs, FPGAs, DSPs. What can we do about it? So we can look at what affects the operational emissions and the embodied emissions, and see what can we touch to reduce both of these parameters. For instance, if we can accelerate our compute workloads, then we might do the same compute with less number of platforms. This means less embodied emissions. If we can improve the energy efficiency of our platforms, this can be done with ASICs, with FPGAs, CGRAs. You see that you can have a much higher energy efficiency per millions of operations. Then you would reduce the total energy consumed during the lifetime of this hardware. It can be 4 years, 6 years, whatever you want to keep it. So then you're going to reduce the emissions from the operation of these platforms. But you also reduce the cost because electricity is expensive, right? So you have a double benefit on making platforms more energy efficient. So this is where we go. So how can we achieve this? Because AI is changing, but all the workloads that we have are changing. So we want some flexibility. So we usually focus on CGRAs, FPGAs, and sometimes they seek to have like the highest benefit. But this is only for workloads that we know are going to stay like that for a long time. So the effort of in building a new chip design is actually amortized. Okay, so let's break down a little bit. What are the different impacts that you have adding up to the total emissions and to the cost of different types of platforms that we have on the market. And you can see that there are different trade-offs. So with the red, we have bad things. With green, we have good things. And well, in black, it's just, well, things that are there. Maybe it's obvious. CPUs are very flexible. You can run any kind of workload, but they're not the most efficient, both in power and time. GPUs, they run faster, so you lower the stress on this term over here. FPGAs, they're super nice. You can many times accelerate both the TDP of an FPGA is usually, I don't know, 20, 100, maybe up to 200 watts, a lot less than a GPU. And sometimes you can manage to do the same work or even faster execution than on a GPU if you can optimize carefully. So it's a very nice sweet point. And for the ASIC, the biggest investment would be on the embodied emissions. This is when you generate a new ASIC, it's not just the ASIC, it's the whole infrastructure and pipeline to actually build it, and you have to build it to produce it at very large scale to justify the investment. But then the power and efficiency improvement, it's really worth it. And this is just for the embodied emissions. You have to also look at the carbon intensity in the location where you operate your data center.
Denisa, the screen shared.
I know. It happens recurrently. I don't know how or why, but I'm gonna keep bringing it back. Thank you, Miguel. It's out of my control. Okay, so yeah, this is something that we need to keep in mind. The carbon intensity of the electricity production in different regions is different. France is doing great. If you go to the US or I don't know, to Poland, it's not so great. Okay, so this motivates the work of the CODC framework. It's a work that it's mostly led by Ben. So if you have anything to add, please go ahead. But the question that we were trying to answer is how to make sustainable growth of computing capabilities in AI data centers economically viable. I know it's a mouthful of a question, but sustainability, we think it's not going to work if it's not going to be viable. So nobody's going to buy something that is too expensive. And this, there are different layers at which we as computer architects, also data center managers and architects can do something. So we identified several levers or balances where decisions can be made. And there is also another group that we cannot really touch, but we can tell them, hey, if you work on the carbon incentives in a way that you align, what would be the ideal price of platforms or of electricity, data centers or just businesses around compute would actually buy the most efficient or the most sustainable platform naturally, and sustainability would be just an emergence of a system that you regulate through policy. So we look at these three squares mostly. So and the main idea is to find a way to minimize the carbon emissions over the lifetime of platforms, and also minimize, or let's say you can maximize the return on investment to make it positive. And all of this is having into account the demand growth projections that you have for AI workloads. What we learned from this study, looking at the life cycle assessment of embedded emissions of platforms. Are you familiar with the MLPerf benchmark suite? It's just like a standard machine learning benchmark where Google, NVIDIA, Facebook, like big players in AI, they're submitting what would be the best performance and energy of deploying different AI models. So we took that as an input, all the context that you need to compute the life cycle and return on investment for different platforms, assuming a cluster of Google GPUs, NVIDIA GPUs, whatever, running that according to the benchmarks. And we studied what factors we can touch at the data center architecture level, at the hardware and software design, and the policy to align these things, the sustainability interests, like reduce as much as possible the kilograms of emissions per compute we do, and also in total, and improve the cost, so that this is something that everyone wants to do naturally. Yeah, these are the main takeaways. That well, it's obvious that you can limit the capacity growth. You don't really have to follow the demand growth, but this means limiting the business you do. You can invest a lot in domain-specific designs. This is where we come in as hardware and software architects. And then you can also see how we can play with the carbon intensity. So choose the platform that is the most effective according to the location. Here's an example of what happens when you have a life cycle of 4 years of a cluster of typical commercial platforms for GPUs. And we defined two metrics: the price efficiency of this platform and the carbon efficiency of it. You want to be on the green spot, so this is nice. If not, you have to to improve somewhat. And you see that there are these contradictory trends, that the embodied emissions keep growing, the price of GPUs keep growing, there is more electricity demand, so it's a difficult situation where and there are very few options that can actually improve the overall carbon efficiency over procurement. If you've made a decision to change, here the study was done from a baseline of V100, I think, Yeah, so we started with a cluster of 1000 V100 GPUs and say, okay, what would be the most carbon efficient and price efficient procurement that you could do to reduce emissions and also not lose money for the lifetime of 4 years, assuming like the average carbon intensity that we have in the world. We did this for more countries, but just to have an overview, like what would be the landscape. And I mean, this is not really obvious what we can do as researchers in hardware software design, but if we were to make a new hardware architecture, new platform design, we can use the same metrics to position our new design and say, okay, we want to make something that falls into this green area so that it's both sustainable and profitable. So this is the reason that we came up with this metrics so that it's easy to see if a design is actually useful for this landscape where we have to design for sustainability as well. Okay, you have any questions until now? Okay. Here's another dimension of it. We look at the demand growth. So let's assume that we have a cluster, again, 1000 GPU nodes, and you want to upgrade according to the global trends that we see on energy efficiency improvements and performance improvements, like the best that is out there on the market, to a new platform. The question is it feasible to grow 5x the compute capabilities of a data center? So what you see here on this map, you have the carbon intensity, the average one at the country level. So you see France, it's super nicely positioned. But then the electricity price is not so great. It's quite expensive to run a data center here in France. But then you go to the US or to China, and then it's super carbon intensive. And then the electricity is mostly carbon based and it's cheap. So it might be easier to keep all the inefficient platforms and not want to get what happened. Yeah. Newer, more energy efficient platforms to get running into your cluster. So how can we achieve this growth in scale? We said one way would be to upgrade to more energy efficient platforms, but we want to grow without increasing the total emissions over the life cycle, including the investment in the embodied of these new platforms. And we see that there is a limitation how much you can grow isocarbon. It's like less than 4x. But if you wanted to grow all the way to 5x, you'd also have to decarbonize the electricity. Maybe you cannot do it for the whole region where the data center, but you can maybe install some PVs or some local renewable sources of energy. And if you manage to do both of these things, so have more energy efficient platforms that get the next best thing on the market and reduce some 20% the carbon intensity of the electricity produced for a data center, then you could manage to grow 5x isocarbon. Let's say we call this sustainable growth. So it's kind of doable. The problem is that according to Paris Agreement, we have to actually reduce, not stay the same. So it's a first attempt to understanding what is the landscape. I'm not sure if to go really deep into this graph. It's the same one as before, but more countries, and then putting the real case when you want to follow the Paris Agreement. So green is our carbon budget for the next 10 years, and pink is the overexpenditure of emissions if we don't do anything to improve the efficiency of platforms or the carbon intensity of the electricity grids. And I mean, there is opportunity. The arrows upwards show how much we could reduce the total emissions by upgrading older platforms that have been staying in a data center and reduce the life cycle by getting newer, more energy efficient platforms. And that's a way to do it. But then the decarbonization roadmap for the grids is crazy. So I don't think it's really viable to do this in practice, but this is what we should ideally do all over the world to follow the Paris Agreement. So it's not too disheartened, but just have an idea of the of the milestone. And what we see in the case of Switzerland and France, that already have very green electricity production, it's not even feasible to do some of these changes. It would be way too expensive to invest in more energy efficient platforms, and also decarbonize. It's getting like marginal improvements over high expenditure of investment. Okay. Any questions about this? All right. Are you sure you want to put this on YouTube? I'm gonna try to share again. Yeah.
Surprised. Worked this morning pretty fine.
Yeah, I don't know what.
Encore. Ça va marcher, ça.
Okay. So this would be a whole summary of what I was telling you. That we looked at the energy efficiency improvement rates or trends for all of these MLPerf benchmarks over the years, and you see that most of them improve quite a bit in energy efficiency, but also the acceleration rate over the last 10 years, it's been solid. And if we were to draw some lines based on these projections from the International Energy Agency of the adoption of AI and the demand growth, worst case scenario is number one over here. And there are still some cases where there's enough energy efficiency improvements so that the upgrades to newer platforms would keep the carbon emissions under what is actually happening. So they will be getting lower and lower. But then the upgrades would have to happen quite not too often. You'll have to keep the platforms for maybe 6 years or so that it's profitable. And this happens because the newest GPU models, which are the most energy efficient and most performant, they're just too expensive. It's a huge investment. This is the main outcome. So there are several mismatches. One is on the price of GPUs, and the other mismatch that we saw is on the cost of carbon. So either as a tax or an incentive to make let's say data center managers or whoever is investing in computing to want to buy the most efficient, not just the cheapest version to upgrade and to scale up. So I think the average carbon tax was $12 or $15 per ton of CO2. But what we got from our study is that this number should be over 500 francs per ton of CO2 to actually make align the mismatch in between, to make it hurt, produce more emissions somehow. So yeah, And there's the other thing that the amount of efficiency that we can get from new architecture improvements and co-design and improving like all you can improve and squeeze as performance and efficiency from AI platforms is still not fast enough. I mean, the improvement rate it's great. It's like 1.5 for most of X per year for most of the platforms, and a little bit under 2x for acceleration. But still, there's a mismatch in between the demand growth, how much you have to improve, how fast you have to improve, and what is actually happening for AI. So we still have to do better. Yeah. So this work on CODC, we submitted it, got rejected, and now we're submitting with IMEC, which are very interested in this work, and they would like to include it into their tool for studying what would be the decisions for growing large-scale computing clusters for CPU. So I would still say it's a success story because, I mean, people want to use it in practice and production. Okay, now I'm gonna jump into the SIMS project because, I mean, all of this started because of SIMS. We wanted to make this study for the data centers that will be powering like the biggest high performance challenge in radio astronomy for the coming decades. So I'm not sure how familiar you are with the Square Kilometre Array. They're gonna have a couple of sites. Well, they're already there, growing number of antennas in West Australia and in South Africa. Here you have the numbers. They'll be operating for some 50 years. That's the idea, and they're gonna produce a lot of data that you cannot possibly store because you don't have this capability you would see here, like some 20 terabits per second streaming when and if they manage to install the whole number of antennas that they plan to. And yeah, we want to do this fast in real time if possible. And then there is a cap on how much power you can use for this because there are going to be two science data processors. We will focus on this in particular. Next to each site. They're cities, but kind of close to the deserts, not very good electricity infrastructure, very high carbon intensity. So our goal is how to make this as energy efficient as possible. That's the mission of the SIMS project. I'm not sure again. Wait a second. Here we are. So out of the three like computing sites, like types that you see, the signal processor is next to the antennas. The science data processor is Perth and where's the other one? Cape Town, I believe. And then they're gonna be like a network of data centers across the world where scientists will just take the image data, which is the product that you have from the science data processor to do science on understanding how the cosmos, gravity, magnetisms, black holes, and so on, all this crazy science that we don't do, we do architecture, but it's motivating that all the work we do, it's for the greater good of pushing the frontiers of science and knowledge. Yeah, so what we actually do is look at these compute kernels that you have in this loop over here and ask ourselves how can we do this as energy efficient as possible, what kind of architectures we can co-design for it, and make some demonstrators for real scenarios. We do this with people at INSA, of course, people from the Observatory of Paris, Côte d'Azur, we have Shan over here, and Sunrise, and then people from ESL, where I'm from, and Ruben and Miguel is online right now, and also we have Citas over here with Etienne, and then of course we always collaborate with people that actually are involved in the astrophysics challenges and like build up of algorithms, because I mean we want the algorithms, we're not building those. And we want to know how can we implement that as efficiently on hardware, or how to design hardware that does it as efficiently as possible. Our approach was, okay, let's use GPUs for fast prototyping for the first 2 years. Now we're working also on CGRA, so we're mapping different kernels on this type of platforms. We look at the possibility to have lots and lots of them, but also with HBM, because you have to access massive amounts of data, and it's mostly like a memory movement kind of problem, not so much of a compute problem in general. And you also have to scale. Like, how do you manage all of this? And that's why we have people working on Prism, like Jacques. That's gonna help us out to figure how to do this kind of accelerators behave nicely with the commercial like CPUs, and like use the resources as efficiently as possible. So we want. Let's see what this brings us to, but I think we're quite hopeful. Okay, I'm not going to go into more details, but maybe by the end of the project we should have another meeting like this and we present the results. But this is the vision of the whole project. Okay, now I'm going to go into co-design tools and methods that we have developed at ESL for AI on the edge, and this includes lots of different kinds of applications. Actually, the approach that we usually have for research is like application-driven kind of research, and having a system level view of, okay, I'm going to make a new architecture for a specific application. We're going to do biomedical monitoring, or we're going to do like real-time navigation of a drone, or like some very specific end-to-end application when you start from collecting data, building the whole setup for collecting it, testing, and actually having a small product that you can test into the field. But these small products, like a sensor patch or smart glasses and so on, they're small. So they have a battery problem. You cannot put a lot of compute. You cannot put a lot of resources. So these are the kind of challenges that we have to do AI in general on the edge. It's always a struggle in between. How do we do large smart models, not dummy like research or stuff like that, on very limited kind of resource platforms. I'm going to give you an example from the Urban Twin project. I'm leading a work on designing scalable, secure, and efficient ICT solutions for this thing. I'm not going to explain all the boxes, but the whole idea is to make a digital twin of a city, an entire city. And this includes the energy infrastructures, the mobility, planning of buildings, wastewater management, the power systems. If you want to grow the city, how you gotta expand this infrastructure. So it's a really big project. Our job is to understand how can we do the sensing, smart sensing of all of these different systems that have different requirements. Like how often do you need the data? Can you make decisions on the spot, like real-time processing and, let's say, alarm system or decision systems? Or do you send it somewhere centralized, like in this Urban Twin tool that kind of covers everything? And there is a lot of different challenges that come out of this project. So I think it's a good example to reason about it. Sharing again. Thank you for helping with that. Okay, then we have a sip of water. Okay, so let's put this in a more systematic way for urban digital twin, like in this kind of project. We can have the option to collect all of the data, send it to a centralized server, and do all of the analysis and provide information for decision making. Like, okay, do we extend? There is a problem. What do we do with this infrastructure from management and planning point of view? But as you saw, there are very different entities. There are groups that do the management of water infrastructure, of electricity infrastructures, and they're different entities altogether, so they don't want to share data with each other. And there's also the problem of latency. So if you want to collect massive amounts of data, you want to send everything to a centralized server, maybe it's not feasible, like the bandwidth that you have available. And if you want to do this in real time, it's not ideal. So that's why we researched for this project, what can we do in the edge? And how much of the computation, like the intelligence, can be brought where the data is collected, not really centralized in a way that would make lots of people unhappy. Yeah, of course, there are some challenges here, like memory, battery, computation, but then you have these benefits that make most stakeholders happy, especially the data privacy one. The problem with doing AI on the edge for such variety of problems of data acquisition is that each one has a different pattern. Like some need very fast sampling, others, like for instance, electricity, like smart meter versus wastewater meters. Like in water monitoring, you're happy with one sample every minute. If you want to do power regulation, you need millisecond kind of sampling to have a feedback loop and control in there. So what we need to do in this case is to optimize each one of these stages for an AGI application, but in a way that is customized. So that's why we need co-design. And I'm going to show you an example of water monitoring for one of the demo sites that we have on the EPFL campus. This is a river at the edge of the EPFL campus, and we deployed a federated learning scheme for collecting data from different locations, identifying if there is some anomaly. So let's say pollution, or then other type of anomaly would be what if one of the sensors is broken or is giving faulty data? How can we do federated learning without sharing the data from all of the sites in a way that is stable and it's not gonna destroy the accuracy and the performance of a global model when there is problem on the site, like one sensor starts to drift, it breaks, sometimes you have a flood, the sensor washes away. So what do you do this? What do you do with it? So we did a quite nice setup on this, and we managed to deploy it on Raspberry Pis. So each node would have a Raspberry Pi, and it kind of worked. So we managed to get a good performance on this. But then when we look at the breakdown of the resource consumption, you see the compute is one important part, but then there is the other part of energy that you don't know where it's going. So it's just overhead of elements that you have on the Raspberry Pi that are not necessarily needed. So you're wasting a lot of energy if you want to have a battery-powered large-scale monitoring system. So this also motivates doing co-design, and instead of using commercial IoT platforms like Raspberry Pi, build our own platforms that can do exactly that task, but with the expenditure of milliwatts instead of watts. And like this, you could have it operating for a year without having to care about it, instead of having to check, recharge, or change the battery every day, which would be the case here. Okay. So how do we do this? How do we co-design for AGI? So there are different abstraction levels from the software to the hardware. Going back. Okay, window. And doing optimizations at each one of these levels is going to have an impact on the performance and on the energy savings. And all of them is going to add up a little bit to it. So you want to optimize at all of the different levels in reality. Like you start with a commercial deployment like the Raspberry Pi, then you specialize your hardware, you co-optimize again your software, and then finally you would have something that is then really energy efficient. And for this we developed the X-HEEP platform, and it's very nice to do this loop. It's an open platform for AGI prototyping, like lots of people are already using it. We also have quite a few silicon prototypes that are live and working. And we build lots of different domain-specific accelerators for AI, like near memory computing, an open edge array of Venn, edge GPUs, variable precision vector units, and so on. And this was integrated in embedded edge AI sensing platforms like VersaSense over here. I'm going to skip this one. Like this is what is in X-HEEP, it's just standard IPs out there, which means it's pretty well tested by the community. Well, to use it, you just go to the documentation. It's quite well maintained. Or you can join one of the agoras. Here you see us, both Ruben and I, and present if you're doing any work with X-HEEP. You can like really get into the community and use IPs that others have built and learn about them. For instance, a Corti accelerator, we have lots of sine and cosines in the imaging kernels. That would be a good baseline to compare against. Or I don't know if anyone of you is doing embedded AI using, you could look at like a GPU, like this kind of examples. And I think, Mikael, you mentioned that there's already some people working with X-HEEP here. So
yes, we've implemented a Toggle program of
yeah, so I think we need to add your logo here.
yes.
I didn't know about this. I just learned it today. But yeah, it would be very nice to have you at one of the Agora meetings. So maybe when I share the slides, you can follow up and you tell us what you're doing, and people around in the community can tell you what they're doing, and maybe you can reuse open hardware research. I will just mention a couple of platforms. One is Hippocrates. It's a typical one that we use in hardware software co-design. So you have the software optimization look over here, and then the hardware resources. How do you do this mapping as efficiently as possible for a particular application of AI? I'm not going to go into detail. Maybe this one, which is quite interesting, the power management unit. I think you also worked on this one on the HPC, right?
On the DMA and the SPI.
Yeah. But for energy efficiency, for instance, the voltage frequency scaling, and you have a different power operating modes. It's something that you can do like further to reduce the energy consumption when you're not using any of the resources. So this is a nice feature when you design your own accelerator and you have to really squeeze all the energy. Here is a VersaSense. I mentioned it earlier, just to see the nicer version of the prototype one in a black box. It's something that's also open. You can just make your own circuit, print it out, put it in a box, and then use it for different setups where you want to do biomedical data acquisition and try to do some AI on the edge. It actually has Hippocrates inside. Okay, I don't have many more than this. This is just like what you have inside of Hippocrates. It's a very, very small chip, as you can see here. My only contribution was the design of I like drawing a lot. Other people contributed with the more technical aspects, but I put it as like a fun fact. here inside, you can see that there is also the CGRA that we started the work on SIMS as a motivation. Hey, this can be super efficient for IoT and for AGI. Can it be as efficient for HPC? Well, this is what we want to find out with the help of Ruben. Yeah, I was mentioning the part on how do we manage all of these resources. For that, we have Medea. Maybe Miguel can tell you about it if you have any questions. But the idea is to do DVFS, so it's dynamic voltage and frequency scaling, and actually selecting which accelerator you would want to use in a platform that is designed with X-HEEP. Like which accelerator would you use for optimizing for the latency that you have as target for a real-time system, and also for the minimizing the total energy consumed for the execution of your application. In this case, the numbers are for a DNN application. Okay, that's it from my side. If you have any questions, please go ahead. I left here the summary of the points.
So if there are any questions in the room or online as well, you can switch on your mic and talk. May even see your face next time your the system still works sharing. Yeah.
I'm gonna maybe stop sharing, and like this we can see people that are remotely.
I have a question about one of the last things you showed actually about the Medea stuff.
Yeah.
So this is, if I understood well, something that helps to manage the DVFS of the different parts of the tool, and how does it work? I mean, is it with a handwritten control policy, or how does it decide to increase the voltage in some place?
Miguel, I'm going to let you take this question because you're a PhD student.
So actually, this is not for Android devices. This is for deeply embedded devices, and we are talking micro or milliwatts of power. So there is normally bare metal environment or free RTOs. And then, yes, it is expected that you can control the voltage and the frequency, the FLL of the platform directly. But Medea does not only control the voltage and the frequency, it also analyzes the algorithms. For example, this example is coming from a transformer application, and then it looks into all the layers of the application, everything that you are doing to try to scale it over the multiple compute elements that you have in the platform. In this case, there was one processor, a RISC-V processor, very simple, on the family of X-HEEP. Actually, it's based on X-HEEP. Then we had the CRA, which is the one on Hippocrates, is the OpenEdge CRA, plus some near memory computing unit. So what it is doing is that for every layer, it is trying to determine if it should be executed on the CPU, on the CRA, on the near memory computing, and at which voltage and frequency point. The thing is that it admits task deadline. So you have to tell it what is the deadline that you have for complete, all the complete, in this case, the application is the transformer. So according to available time, it will try to minimize the consumed energy. And of course, if you are given a very, very tight deadline, like for example, the 15 milliseconds example, it has to go to the highest operating points. It doesn't matter what is the energy that you are using. But you give it some slack on time, then it can start trading execution time for energy consumption. That's basically how it works. But it's for deeply embedded systems.
Okay.
Thank you.
Thanks for that.
You're welcome.
Okay. Any other curiosity? Okay.
Is a question? Or did you have a question? Yes. Go ahead, Paul.
Okay. Please.
You have your mic off.
Can you hear me?
Yeah, sure.
Okay. First off, thank you for your very nice presentation.
Thank you.
I was much expecting it because I'm using X-HEEP. and I'm the only one in the lab. So it's good to have some feedback on X-HEEP. I think the way I used X-HEEP is not in the current trend that AI co-design is made. Because as we just saw with DVFS and transformer execution, current AI systems are trying to build around the accelerator, which is the main trend. So you have your CPU and you power gate everything as much as possible, and once you run the computation, you power everything on for a very short amount of time with a very high frequency, and the computation is made. What we did here in this lab is a totally different approach, where you don't need to build a specific accelerator. You don't need the accelerator at all. So I did a co-exploration rather than co-design. So what I did is that I took the RISC-V processor cores and just explored on those cores using X-HEEP. So we are using the different cores of X-HEEP, but just as they are without any ISA extension or coprocessor or anything for the exploration of our latency. And we have good results in terms of latency when compared to other AI tools. But the point also is that ideologically, we do not create a new accelerator, and we do not need to print a new chip so that we can reuse existing chips.
Okay. I mean, I guess this depends a lot on the type of application that you want to accelerate. For some cases, a CPU core is the best option, and there you cannot do a lot to improve with the custom accelerator. But do you have a specific question? Is there something about your application that would make?
No, it was just to say that we are currently trying to challenge the point where we go from the CPU to the accelerator. The co-design point where we think that the accelerator is needed. We are trying to challenge that, and it was just a little remark on this, because your slide is much targeted around the sustainability. And what the carbon cost of the new chips is, and I think a big part of this lab is trying to challenge that as well. So it's most complementary, I think.
Yeah, but it's not really a different sense. We build accelerators when there is actually a good reason to do so. If there is a limitation on standard CPU or existing accelerators, you have to do something else to overcome this, because you have to meet some energy or time budget. But if there is no limitation on the existing hardware, of course you're going to use that. There's no point in investing time and energy to make something that is not going to bring you any benefit. So I think your approach is totally right, and understanding for which application there is no need to actually move to a GPU or custom edge AI accelerator to help people decide, okay, for this case, the CPU is good enough, and is it out of the box? I think that is totally the right choice. Yeah, go on here.
Yeah. If I may add something, that would be very interesting to actually learn when you have some results, to learn about them and see what you are doing. Just the only thing that we have seen is that very often when you actually need to do some computation, it is way more energy efficient to do it on the accelerators. Like, for example, in Hippocrates, the CRA of Hippocrates, which is the OpenEdge CRA, there the power of the accelerator is quite higher than the power of the CPU. But if you achieve enough speed up, then the total energy of the system is much lower because, for example, you are removing the static leakage of a lot of components when you can go to a power gated state more often. So that's actually what we observe, but it's of course interesting to know different applications, different cases. And also we have an experiment which is not yet published, where we actually have several versions of the CRAs, several different CRAs. One is OpenEdge CRA. The other one is called Disco, which is actually integrated in one of the next iterations of X-HEEP, which is called Hypatia. And that CRA is much larger. It has very wide registers. It has an internal scratchpad memory. Plus, it contains dedicated cells, so it's heterogeneous. And what we have observed is that when the algorithm is complex enough, it is actually better to use Disco than the OpenEdge CRA. However, if there is not enough complexity, it's much worse because it has a larger area. So you paid for the cost of the area, of course, in the silicon, but then also you are not enjoying the speed up on the computation. So you pay for larger area, is a larger leakage. So you really have to understand when you want to integrate one or the other. So it will be very interesting to read about your research when you have it a bit more mature. Please keep us updated.
Yeah, we are accepted at Computing Frontier. We are submitting the final version this week, so we share that as well.
Excellent. And then, as Denisa said, we extend the invitation to the next X-Agora. So what we will do is that when we have a new date for the X-Agora, we will forward it to you. If we don't have your contact, we will forward it to Michael or Jean-Francois, for example, so that they can forward it to you. And then you can join freely. Normally in the Agora, what we have is that every group that is interested in presenting what they are doing with HEEP for every other people to know, they can present one slide and they have 1 or 2 minutes to present their research, simply for people to be aware. And then you will be able also to know all the different types of accelerators that people are doing for different tasks in the platform. So glad to know you, Paul.
Glad as well. Thank you very much.
Okay. Any more questions? Okay.
No, it's fantastic enough.
Thank you.
Thank you very much.